Roman concrete has been sitting underwater for 2,000 years, and it is getting stronger. Modern concrete, the kind holding up every bridge, every highway overpass, every parking garage in the world, starts crumbling in 50 years. Some of it fails in 30. Engineers budget for it. Insurance companies price it in. Governments allocate billions every decade just to patch what they built the decade before. But Roman sea walls constructed in 37 BC are still standing, perfectly intact, in salt water, under wave pressure, for 2,060 years. In 2023, a team of researchers at MIT published a study that identified exactly why Roman concrete becomes stronger over time rather than weaker. The paper sent quiet shockwaves through the material science community. And then the construction industry said almost nothing. No headlines, no emergency Senate hearings, no governor announcing they would rebuild their crumbling infrastructure with this ancient formula. Just silence. Because the global cement and concrete industry generates $340 billion every single year. And what they discovered in those Roman harbor walls is the one thing that business model absolutely cannot survive. This is the story of the strongest building material ever made. Who discovered it, why it was abandoned, and how you can use it yourself today. Part 2. Historical discovery. Let me take you back to the year 37 BC on the coast of what is now southern Italy. Roman engineers are standing at the edge of the Tyrrhenian Sea with a construction problem that would make modern civil engineers sweat. They need to build a harbor at Caesarea Maritima, a massive port facility capable of handling the naval traffic of an empire. And they need to build it underwater. Modern concrete cannot be poured underwater. It requires dry conditions, formwork, curing time. It dissolves in salt water before it sets. This is not an opinion. It is a fundamental chemical limitation of Portland cement, the compound every modern structure is built from. The Roman engineers did not have this problem. They mixed volcanic ash from the region of Pozzuoli, a gray powder called pozzolana, with seawater and lime. They poured it directly into the ocean. And it hardened, not despite the seawater, because of it. The resulting material is called opus cementitium, and for 500 years it was the backbone of Roman infrastructure. The Pantheon's unreinforced dome, still the largest unreinforced concrete dome on Earth after 2,000 years. The Colosseum's foundation, absorbing the weight of 80,000 spectators for 2 millennia. The harbor walls at Caesarea, Cosa, and Pozzuoli, built in open water and still measurably intact today. Roman engineers did not fully understand the chemistry. They knew the formula worked. They passed it down through generations of military and civil engineers, documented in the writings of Vitruvius around 30 BC. His 10-volume work, De Architectura, describes the precise ratios, 2 parts pozzolana to 1 part lime, with the confidence of someone recording a fact so obvious it barely needs stating. Then the Western Roman Empire collapsed in 476 AD, and the recipe disappeared with it. Not destroyed, not banned, simply forgotten as the institutions that carried the knowledge disintegrated over 2 centuries of fragmentation and invasion. Medieval builders used Roman ruins as quarries, hauling away the very structures they could not figure out how to rebuild. For 1,400 years, the strongest building material ever invented sat waiting in the volcanic hills of southern Italy, unused, misunderstood, occasionally rediscovered and then lost again. Here is why it works, and this is the part that should make you stop and think very carefully. Modern Portland cement, patented in 1824 by a British bricklayer named Joseph Aspdin, hardens through a process called hydration. Calcium silicate compounds in the cement react with water to form a rigid, crystalline structure. The process produces significant heat, locks into place within days, and then stops. Once cured, Portland cement is essentially chemically inert. It just sits there. It does not adapt. It does not repair itself. And crucially, when it cracks, which it always does, those cracks become pathways for water, chloride ions, and freeze-thaw cycles to progressively destroy the structure from the inside. The average lifespan of a Portland cement structure in a marine environment is 40 to 70 years before major structural rehabilitation is required. Roman concrete does the opposite. The MIT study published in Science Advances in January 2023 identified the exact mechanism. When seawater percolates through Roman concrete over centuries, it reacts with the volcanic ash to form new minerals, specifically a rare crystal called tobermorite, that grow inside the existing microcracks and actually fill them in. The concrete heals itself. Not metaphorically, literally, measurably. The mineral crystals grow into the fractures and reinforce the material at the microscopic level. The longer Roman concrete is exposed to seawater, the denser and stronger its internal crystal matrix becomes. The key ingredient is the volcanic ash. Specifically, a luminous tobermorite formation requires the unique chemical profile of pozzolanic ash, high in aluminum, reactive with calcium, and capable of forming stable crystalline structures at low temperatures when combined with seawater and lime. Pozzolanic ash is not rare. It is found across Italy, Greece, Turkey, Iceland, and significant volcanic regions of the western United States. Mount Rainier's region, the Cascades, the volcanic fields of New Mexico. The raw materials for the strongest concrete ever made are sitting on the surface of the earth, available, inexpensive, and geologically abundant. Now here is the part nobody in the construction industry wants to discuss openly. Portland cement, the modern standard, was not adopted because it was superior. It was adopted because it was faster and because it created a manufacturing dependency that volcanic ash simply cannot. Joseph Aspdin's 1824 patent created the template. You mine limestone, heat it to 1400 degrees Celsius in a massive industrial kilns, burning enormous quantities of coal or natural gas, grind it into powder and sell it in bags. Every single pour requires fresh cement from a manufacturing facility. There is no substitute. There is no local alternative. You cannot dig up Portland cement from a hillside. You must buy it. The global cement industry produces 4.1 billion metric tons of Portland cement annually. The manufacturing process alone accounts for approximately 8% of all human carbon dioxide emissions worldwide, more than the entire aviation industry. And every structure built from it begins degrading the moment it cures. The American Society of Civil Engineers estimates that the United States alone requires $2.6 trillion in infrastructure investment over the next 10 years, largely to repair and replace existing concrete structures that are failing on schedule exactly as the economic model requires. Bridges, highways, dams, water treatment facilities, ports, all of them built from a material engineered for a lifespan, not for permanence. Roman concrete does not fit this model. You cannot build a $340 billion annual industry around a material that lasts 2,000 years and gets stronger over time. The math does not work. A harbor wall that never needs replacing is not an asset to a construction economy built on replacement cycles. It is an existential threat to one. The MIT research did not happen in isolation. It confirmed what geologists and archaeologists had been documenting for decades. In 2017, a team from UC Berkeley published a separate analysis of Roman harbor concrete from 17 different Mediterranean sites. Every sample showed the same pattern. Tobermorite crystal formation increasing with age, structural integrity measurably improving over centuries. The study recommended urgent investigation into pozzolanic concrete formulations for modern marine construction. That recommendation has not resulted in a single major infrastructure project using Roman formula concrete anywhere in the world. In Iceland, where volcanic ash is locally abundant and the coastline is brutally exposed to North Atlantic conditions, a small number of experimental seawall sections were built using pozzolanic lime ash formulations in 2019. After 5 years of monitoring, the experimental sections show markedly lower surface erosion than adjacent Portland cement sections built at the same time. The experiment was documented in an Icelandic civil engineering journal. It has not been scaled. In the DIY natural building community, lime pozzolan mortars have experienced a quiet revival over the past 15 years. Builders working in restoration of historic structures and natural building enthusiasts have been independently rediscovering Roman formulas, sharing results online, and documenting multi-year performance data. Their conclusions consistently mirror the academic findings. The material works. It works exceptionally well. And the raw materials cost a fraction of commercial Portland cement. Here is what you can actually do with this knowledge, and it is more accessible than you might expect. For masonry, garden walls, outdoor structures, and restoration work, a pozzolanic lime mortar can be mixed and applied with basic tools and materials available from any masonry supplier and many agricultural suppliers. You need 3 things: hydraulic lime, also called NHL lime, available from masonry supply companies for approximately $15 to $25 per bag; pozzolanic aggregate, volcanic pumice, trass powder, or metakaolin, available from specialty masonry suppliers or online for comparable cost; and water. The basic ratio mirrors Vitruvius exactly. 2 parts pozzolanic material to 1 part lime by volume. Mix with enough water to achieve a workable consistency. No industrial kiln, no specialized equipment, no proprietary additives. For outdoor applications, garden walls, retaining structures, stone restoration, pathway edging, this mixture outperforms Portland cement mortar in freeze-thaw resistance, vapor permeability, and long-term bond strength on natural stone. It is also self-healing at the micro-crack level, just as Roman concrete is, because the chemistry is identical. Total material cost for a standard garden wall project runs approximately 30 to 50% less than Portland cement mortar, with better long-term performance. For anyone working in restoration of a historic brick or stone buildings, lime pozzolan mortars are already the professional standard in conservation architecture precisely because they match the movement and breathability of original historic materials. The knowledge exists. It is practiced. It is simply not the default. There is a Roman seawall in Caesarea that has been underwater since before Julius Caesar was born. Modern engineers inspect it periodically. They take core samples, they measure, they write papers, and then they go back to specifying Portland cement for the next bridge, the next seawall, the next harbor, because that is what the supply chain delivers, what the building codes specify, and what the industry has trained every engineer to default to for 200 years. The strongest building material ever invented is not locked in a vault. It is not classified. It is not protected by patent. The formula is in a 2,000-year-old book that anyone can read for free. What separates us from using it is not chemistry. It is not engineering. It is simply the economic architecture that was built around a lesser alternative, because the lesser alternative could be sold, metered, and depended upon in ways that 2-part volcanic ash and lime never could be. Some knowledge does not disappear. It just waits at the bottom of a harbor, getting stronger every year until someone decides to remember.